A furniture company makes and sells tables and chairs. A chair takes 5 workers to make, and a table takes 9 workers to make. There are 100 workers available each day to make furniture. It takes 3 salespeople to sell each chair, and 4 salespeople to sell each table. The company has 53 salespeople. The company wants to determine how many tables and how many chairs they can make each day. Have a look at example 3.2 for the setup to this problem, and then come back for part B. Chairs are sold for $42 and tables are sold for $83. So how many tables and chairs should be made? Again, we're assuming that we want to maximize the profit here. So in example 3-2, we set up our decision variables and we set up our constraints. So how many chairs and how many tables should be made? What steps are we going to take to solve this? Well, we need to figure out, first of all, what is the objective function? What are we actually trying to maximize? We need to figure out the corner points, so we need our feasible region. We need to figure out which corner point is best, and make a concluding statement. So let's go through that process. The objective function, pretty straightforward, 42x plus 83y. $42 for every chair. The chairs were x, the number of chairs, and $83 for every table. There are y tables. So that's my objective function. Second, let's find our corner points. Those are the corner points. I will leave that as an exercise for you to graph that system of inequalities and find those yourself, but that's what we should come up with. Which corner point is best? So once again, we're going to plug each one of these 4 corner points into our objective function, which is 42x plus 83y. We get values of 0, 877, $922.22, and $742. So the highest or the best choice we've got is this one. They should make no chairs and 100 over 9 or 11.1 tables. Stop and think about that for a second. Does it make sense? Can we make part of a table? And the answer is not a simple yes or no, because maybe they make 11.1 today, they make 11.1 tomorrow, and eventually they will have made that full table. But there are some cases where the solutions, so the corner point, whatever value we get for our optimal solution, has to be an integer. This is again a bit of an extension. You will see this on occasion, but really don't continue with this video unless you are pretty happy with everything so far. Okay, if you're still here, it means you want to learn a little bit more about how to deal with integer solutions. So what do we do if our decision variables have to be whole numbers? If we can't have fractions, we can't have decimals. So it's a specific thing, and I say, no, I have to make exactly 11 or 12 or 10 chairs. I can't make 11.1. They've got to be all made by the end of the day. What do I do? What you do is you highlight the integer points around each of the you highlight the integer points around the optimal solution. The optimal solution might be the one that has the decimal in it. So 100, what was it? It was 0, 100 over 9. So figure out what integer points are around there. Check which of those points are actually in the feasible region, and then test those integer points to figure out which one is the best of them at least. So here I've got a graph of that tables and chairs problem, and we saw that this point up here was my optimal value. That was my best solution. That was the best I could hope to do. But again, we're saying we can't make 11.1 chairs. We don't like that. Or 11.1 tables. So, the optimal point is 0, 11.1, but that's not quite good enough. So what we have to do is we want to look at the points surrounding 11.1, comma 0. So we'll look at the point below, maybe the point over, above it. Each of these points here that is an integer point. So try 0, comma 11, that's this one that's just below. 1, comma 11, so that'll be over here. Maybe 0, 10 down there. 1, 10. You might also want to try a couple with 12 up top. Again, just to see what might work and what's going to be the best. Well, these 3 points here, I'm just going to change colors for a second. These 3 points here are very clearly not in the feasible region, so we don't need to bother testing those. And this is where a graph comes in handy. You can see if they're not in the feasible region. Otherwise, we can test, do they satisfy all the inequalities? If they do, they're in the feasible region. If not, tough. So we can get rid of all of those, and we're left with, we want to test those 3. So we plug each of these points into our objective function, and we'll find that 0, 11, which is that point there, is the best choice. It's not going to be quite as good as 0, 11.1, but it's as good as we can get making a whole number of tables and a whole number of chairs.